So welcome to this session. Today we are going to have a shear diagram applied on the beam having an internal hinge or a roller. So let us have this first example. So in this example, it is fixed at A and the compound beams AB and BCD are joined through the hinge at B. So those are the loadings. So we are going to establish the shear diagram. So first and foremost, we need to separate or detach the hinge on the beam so that we will be working with the free body diagram of AB and BCD. Okay, we're going to split that. Place your internal reaction, of course, because your hinge was already detached, so therefore reflect these reactions. And then your reaction at A. So we note here that all of these directions are assumed initially. Okay, so moving on to the next part of the beam BCD, we also reflect the internal reaction here. So RBX and RBY is the same RBX and RBY on this right portion of the beam, but it is oppositely directed. Okay, so from that we proceed to RC. So RC is a roller, so we'll just have a single reaction of that roller. And then we could already resolve this uniform distributed load. So we note of the length 2.5 plus 1.5, that is 4, to be multiplied by this 5 kilonewton per meter. So we have 5 by 4 is equal to 20. Okay, so with this, we can now choose between the two. Where can we get unknowns, or we can solve unknowns. So if we are going to choose this side, there will be more unknowns here comparing to the right portion. Of course, obviously, we are going to consider first the right portion, and then whatever values we can get, okay, we will just transfer it on the left portion. So that is the sequence of our solution. So as usual, we are going to have to take moments at B and then solve for RC, take moments at C and then solve for these reactions. So first and foremost, RBX here is a horizontal one, and it is pretty obvious that there will be no horizontal reaction here, so you can just set that to 0 as well as that one. So we take moments at B. We have a clockwise 12 here times its moment arm 2, and this 20, or the result of this distributed load, concentrated on the mid. Okay, where's that mid? So basically we know that this is 2 because that is the half of 4, and then this distance here is the excess from that of the 2.5. So the moment arm of 20 from B is 2 plus 2, that is equal to 4. Okay, so for RC, we have a counterclockwise RC, and the moment arm is 4.5 meters. So all of this shall be equal to 0. So solving for RC, we have that one equal to 23.11. Okay, so from this RC, we can also now employ the value of RBY, that is by applying equilibrium equations on the vertical. So we can say that negative RBY, that is downwards, another downwards 12, and then another downwards 20, plus an upwards RC, which is actually 23.11, and this must be equal to 0. So solving for our RBY, we have a negative value of negative 8.89 kilonewtons. Simply implies that we have a wrong assumption. So this is supposed to be going upwards. So anyway, we'll just maintain the drawing and then just indicate it in your drawing, the sign of the numerical value. So we place it there, and then next we are going to proceed with the left portion. So placing here the forces, we solve for RAY and MA, and of course this horizontal here is also 0. So starting with our moment at A, we can solve that by taking moments at A. So here we have a clockwise MA less the 50 counterclockwise couple less RBY, because RBY is counterclockwise. However, we should reflect also the sign times its moment arm of 2.5 meters. And then all of those will be equal to 0. So solving for MA, we have 27.78 kilonewton meter. Okay, so for our RAY, we take the horizontal or the vertical equilibrium equation. RAY is going upwards plus an upwards RBY, but that is negative. And then that would be equal to 0. So by transposition, we can just say that RAY is simply equal to 8.89. So with this, we'll just have to place all of your reactions on the whole beam, which is not detached. So this time we are going to consider the whole structure. So we'll just place here what we have obtained on ME, and then for RAY, that is equivalent to 8.89, and our RC equivalent to 23.11. We will now proceed to our shear diagram. We first project all of our span. This is the zero line of the shear. So we start with from A to D, or from left to right. So just left of A, we have a positive 8.89. And then we're going to proceed rightwards, and on that we have no concentrated load or any distributed load from A to B, only the couple. And remember, the couple has no effect on our shear diagram. And so from that point, it will remain to be 8.89 up to that point. So anyway, your hinge now is attached. Therefore, we do not we still disregard the internal forces along your hinge connection. And just the same, it will remain to be 8.89 until we deduct 12 units downwards from this ordinate. So we'll be having negative 3.11. Of course, we'll place here the closing line. And then we consider the area of the load diagram from this point up to point C, because point C has a pointed load. So remember that in shear diagram, we always consider a pointed load. So we always stop or halt to a point where there is a pointed load, such as concentrated load. So doing that, we have negative 3.11 minus the area of this rectangular distributed load, that is 5 by 2.5. So 5 by 2.5 is 12.5, but considered to be downwards, that is negative 12.5. minus 3.11, we will be having negative 15.61. Okay, so we connect that by straight line until 23.11 is applied to push this by 23.11 units going up from negative 15.61. So negative 15.61 plus 23.11. So it will yield to a positive value 7.5. Okay, we just connect that by a straight line, and then finally we have 5 by 1.5 for the area of the load diagram to be deducted from 7.5. So 5 by 1.5 is actually 7.5. So that will just close it to 0. So here is our shear diagram. So moving on to our moment diagram. See, this is the moment line. So starting from left to right, at A, we have an initial couple equivalent to 27.78, and that is a positive bending. So we have 27.78, and then from that we are going to deduct this or add this positive area here. Okay, so the base of this rectangular section is 2 plus 1.5 plus 1, that is equal to 4.5. So 4.5 times 8.89 is actually 40. So 40 will be added to 27.78. Okay, so before we place that one, let us check or notice that we have a couple here. So we usually terminate just as what we are doing in the shear diagram, that we halt on a point where there is a pointed load. So in the moment you halt where there is a couple. So basically we will just compute first or add first an area before this couple at this point. Okay, so we'll just consider this for a while. So this area is 1 by 8.89. So 27.78 plus 8.89. We have positive 36.67. So just left of this portion, this is the value until it will reach or it will apply the 50 couple here, that is counterclockwise. So basically 36.67 minus 50 is the ordinate just right of this segment. So the value is negative 13.33. So we just connect the points by a straight line, and then another positive area of this rectangle. So the rectangle here with the base of 2 plus 1.5, that is 3.5 by 8.89, that would yield to 31.12. So 31.12 will be added to this negative 13.33. So it will yield to 44.45 value. So we just connect that by the straight line, and we will just have to correct that value. So it's supposed to be 17.78, and then from this we deduct the area of this trapezoid, and then if you compute that, that would yield to 23.4 negative area. So from 17.78, let us deduct 23.4. So we have here negative 5.62. And then of course, negative 5.62 plus the positive triangular area, 7.5 by 1.5 divided by 2. So actually that would have an area of 5.62 also. So of course it will go back to 0. So knowing that, we will just connect these lines here. So we have here a decreasing, so the connector is concaving downwards with a second degree curve and another second degree curve concaving downwards. So this will be our moment diagram. Okay, so that is how to do this. Okay, so let us try another problem. But before that, we are going to emphasize that on the internal hinge, we have initially calculated the internal hinge reaction at B. Okay, so notice that that is or negative 8.89. However, it should be a positive uh, magnitude, because negative simply just implies wrong direction. Okay, so anyway, that is 8.89. Notice here in our derived shear diagram, it's really 8.89. Okay, so that is the internal effect of those external loading. So moving on to another problem. So on this problem, we have a cantilever support or restraint support at A, and BC will be connected into this beam through a hinge. And then aside from that, it will be having also a hinge at C. So there will be an internal hinge here. So just the same, the first step is to look for the reaction and then consider separation of the two beams connected by hinge. So we usually detach that one. We detach the two, reflect the internal reaction here, the internal reaction there, the internal reaction on the right portion. But note that this is oppositely directed, and then the two reaction at this pin connection. So this completes our reaction. So next is to work with the free body diagram, whichever is convenient here. And obviously, we will be having this one as much more convenient rather than using this one. So considering this right portion, the free body diagram denotes that there is no external horizontal force. Therefore, these horizontal reactions will just be equal to 0. Okay? And then we wanted to resolve the distributed load here. So note that the base is 3 plus 1, that is 4, times the height of 15. So that is actually equal to 60. And then as usual, we take moments at both supports to get the other supports. Summation moments at B, we have this 60 times the moment arm 2 meters. So these are the distances, less RCY times 3, and that would be equal to 0. So therefore, RCY here is 40 kilonewton. We do similar procedure to that of the other reaction by taking moments at C. So this 60 will have a counterclockwise moment with the moment arm of a meter, and a counterclockwise RBY times moment arm of 3. That would be equal to 0. So therefore, RBY shall be equal to negative 20. So you know the meaning of that negative. So we have just assumed that that is downwards and apparently negative value, meaning RBY should be going upwards. So anyway, again, we maintain the drawing and then stick to the units of the reaction. So we place our values, transfer it to the left portion of the beam. So this is also negative 20. This as well as 0 value. okay, together with RAX. Okay, so we are going to determine our MA and RAY. So first, MA, summation, moments at A, we have negative MA. So of course, we resolve this. That is actually 15 kilonewton per meter times 2 with a result of 30. So we just add that effect. And for RBY, it will have, or it will tend to rotate a counterclockwise rotation. So we denote that by negative. Okay, but carry the sign of your RBY. So the moment arm is 2 meters, and this will now be equal to 0. So finally, we transpose this MA to the other side, becomes positive, and then we just sum up this one. This is 20 times 2, 40 times plus 30, or this will become positive 20 times 2 times negative positive 40. It will yield to 70 kilonewton meter if added to 30. Okay, so we have obtained the moment, then we proceed to the RAY. RAY could be obtained by taking equilibrium equation on y-axis. So RAY is positive minus going down 30 plus going up negative 20. So all of those shall be equal to 0. So we have here RAY is equal to 50 kilonewton. So again, we place the values, the 70 and the 50. Okay, so again, we are going to connect these two beams and then reflect all the external reactions we have obtained. Okay, we have the 50 here, the 70, and the value of 40. Then we project the segments and start to graph the shear. Okay, so from A, we have positive 50 here, and then we deduct this rectangle, and that rectangle is 5 by 15. That is actually equal to negative 75. So from 50, we deduct negative 75. So we have a negative 25 value connected by a straight line until 40 will push it upwards by 40 units. So that is positive 15, and then this area here is 15 by 1. Okay, so it will just close our shear diagram to 0. So this is now our shear diagram. Of course, we are concerned with this point. So we denote this as x so that we can use by ratio and proportion. And this triangle as 3 minus x. So by ratio and proportion of similar triangles, we have x is to this height, okay, in which we can also determine this height. So how shall we determine that height? So of course we go back to the area covered from A to B. From A to B we have a 2 meter base, and that will be multiplied by 15. So 15 by 2 is 30, okay? And that is going downwards, that is negative 30. So from 50 minus 30, this is actually positive 20. So place it there as 2. 3 minus x is to 25, solving for x. X is equal to 1.33, and 3 minus x is 1.67. So for our convenience, we can compute each of the areas here. Say this is area 1 for the trapezoid, area 2 for the positive triangle, the area for the negative triangle, and the last positive triangle for the fourth area. So area 1 shall be calculated by the trapezoidal formula, 50 plus 20 over 2 times the height of 2. So that will just be cancelled. So we have 70. So area 2 is a triangular one, 1/2 base times height. Height is the x. So that is actually the x. So we'll yield to 13.33. And then for the negative area of 3, we have equivalent to 20.88. And note that this is negative. And then for 7 area 4, which is 1/2 1/15. We now proceed to the moment line. So we start with A having a negative rotation equivalent to negative 70, and then we're going to add this trapezoid, that is 1. Okay, from negative 70 plus 70, it will yield to 0 here. And for area 2, we'll just have to project this line here and then get the positive 13.33. We add it from 0. Okay, and then we deduct area 3. We have negative 7.55. And eventually area 4 will close it to 0. So we have here a slight difference because of the rounding of numbers. Anyway, this will just close our moment to this point. So eventually it has two intersections on 0 line. So we will just connect this line by its line connector. From this one, this is a decreasing first degree curve. So when we have a decreasing, we have the direct relationship between shear and moment, that is concaving downwards. And basically this is our shear or moment diagram connected by this second degree curve. So this shall complete our moment diagram. Okay, so this shall complete our examples for the day, and I hope you have to go over with this procedure through examples or through problem solving. So to sharpen your knowledge is again to solve at your home. Okay, with this, thank you for listening, and so long.